exponential and the natural exponential functions. Okay, so what is an exponential function? It's any function that can be written in the form y equals b to the x. So, in this case, b is a constant. So b is a constant called the base of the exponential function. It's holding up your exponent. B is assigned such that it has to be greater than 0. And, so therefore it has to be positive, and it can't equal 1. Because if it equaled to 1, we would have 1 to the x, which for any x value would equal 1. So that's why b can't equal 1. Alright, so here we have some examples of exponential functions. To the left, we have f of x, which is 4 to the x, g of x, which is 2/3 to the x, m of x, which is 3 to the x plus 1 minus 4. So, first we want to evaluate f of 3, which would be 4 to the third, which equals 64. And then g to the second, which is 2 over 3 to the second power. So you square the numerator and the denominator like your power to power rule from exponents, and you get 4 over 9. Now, for the function m, we have transformations. So the parent function in this case is at 3 to the x. So if we thought about what we did last time with transformations, or last chapter, we have transformations with the x and then transformations with the y. So anytime it's with the x, it's your horizontal transformation. Anytime it's outside with the y, it's your vertical transformation. And this is even easier to notice with exponential functions, because if it's a small number in the exponent with x, therefore it's a horizontal shift, or if it's a big number outside, you know it's a vertical shift. So remember, all horizontal shifts are opposite, so this is actually left 1. And then that minus 4 is down 4. So a big difference between linear and exponential functions is that in exponential, we're talking about a ratio. And the ratio needs to be constant. So for example, a ratio could be 3. I'm going to multiply 3 each time. So I have 3 to the 1, which is 3, times 3. Let's write that down. So we have an x value of 1, so we get 3. We have a y value of 2, you get 9. 3 to the 3 is 27. So there's not a constant difference like you thought about with linear function. This is just a constant ratio. So the fact that each time we multiplied by 3, that means it's exponential. Okay, so let's look at this example. We have a ball that's dropped from a height of 36 feet, and after each bounce, it reaches a height that is 3/4 of the previous height. So that's our constant ratio. Okay, so how high is the ball after hitting the ground once? So 3/4 times 36, because 36 is how high it came initially, and we know that the first bounce is 3/4 of that. So this value is 27 feet. And we can actually add that down here in our table. At 0 bounces, it's 36. That's where it starts. At 1, we know it's 27. Now at 2, so you would take 27 and multiply it by 3/4. You would get 20.25. And then you would take 20.25, multiply that by 3/4, and you have 15.1875. So each time, each y value to each y value, you have a constant ratio. Okay, so now we're going to graph this example, 36 times 3/4 to the x. So I'm actually going to count by 4s on my y-axis. And I'm going to count by 0.5s on my x-axis. And make sure that you label your axes accordingly. Okay, so looking back at that table, I have the point 0, 36. So this is where the ball is dropped from. Then I have the point 1, 27. So it's about right here. Okay, so I plotted each of my points, and now I'm going to draw my exponential curve. Sorry, my exponential curve. Okay, so here it is. And something else to point out is that you have to notice that in exponentials, our height, so this arrow all the way to the right, will never reach 0. And this is important because you continuously take 3/4 of the height. So if you continually take 3/4 and 3/4, even if the number is so small, you'll still be able to take 75% of whatever small little height that ball bounces. It's also important that you remember your rules of exponents that are listed here below. And even though the variable's in the exponent now, these rules still apply. Okay, so here we have an exponential growth example, y to the 2x. So if you plug this into your calculator, it's important to choose some values that when you plug them in for x, then you get y that you can graph. So some of these, we're going to create our own little xy chart, and we can do most of this in our head since we can work with a base of 2. So if I had the point -1, then I know, according to the exponent rules, if I had 2 to the -1, that would be 1 over positive 2. So I get -1, 1/2. And I'm going to graph that right here. Then I want to choose 0, and 2 to the 0, or any base to 0, is always 1. So you have 0, 1. 2 to the 2 is 4. Oh, I skipped 1. Yes, 2 to the 2 is 4, but 2 to the 1 is 2. So if I plug in 1, I get 2. And then I want to go 2 to the 2 is 4. So I plug in 2 and I get 4, which is up here. And I could even go one step further and say that 2 to the 3 is 8. And then in my book, as long as you see the curve, which I do here, I see the exponential curve, then you just need to choose as many points as you can graph that allows you to see the curve. Another aspect of exponential functions is an asymptote. An asymptote is a line that the graph gets really close to but doesn't touch it. And with exponential functions, they have a horizontal asymptote. So when we have just the parent function, our horizontal asymptote is always at y equals 0. So just like the ball bouncing problem, 0 will never be touched. The y equals 0 line will never be touched by this graph. And again, this is our horizontal asymptote. Okay, so now let's look at an exponential decay problem. And we have an exponential decay of 1/2. So the fact that b is less than 1, but remember, greater than 0, but since it's less than 1, this means it's going to be a decay problem. So I'm actually going to start here by first writing, whether it's growth or decay, I still have a horizontal asymptote at y equals 0. Very important. And honestly, I like to graph my asymptote first and then plot points, just to make sure that as I'm plotting points and when I draw my curve, I know it is not allowed to cross that line. So I usually like doing that ahead of time. So knowing with our exponent rules that 1/2 to the x is the same thing as 2 to the negative x might be helpful when choosing your points. So again, if we have our x, y chart, let's pick some values that we can plug in. So we have, let's choose, what's my first point? So let's choose -3. So this would be 1/2 to the -3. So if I looked at 1/2, this is how I would say it, which would make it, okay, well, since it's to a negative, I need to flip it, which would turn into 2 to the 3, which is 8. So that's our value up here, -3, comma 8. Now, if we looked at this equation right here, we would have 2 to the -3, which would be 2 to the +3, which would also give me 8. So it all depends on how you want to tackle the problem. Okay, let's now choose -2. So that would be 2 to the -2, which would be 2 to the 2, which is 4. So at -2, we have the coordinate point -2, 4. And then this would continue, and I can continue with -1 and 0. -1 would be 2. 0 would be 1. And then if I want to go one step further, 1 would be 1/2. And I have enough here that I can make a curve for exponential decay. So essentially, if your b value is greater than 1, it's going to be a growth problem, which means that your function increases as we go left to right on our domain. And then for exponential decay, our b value is less than 1, but it's still positive because we don't have any negative b values, which means the function is decreasing as we go left to right on the domain. So some things to note with these parent functions, because these are two examples of exponential growth and decay problems that haven't been translated at all. So they are considered the parent functions. They are 1 to 1. The domain is always all real numbers. Notice how they both have a y-intercept of 0, 1. Their range is 0 to infinity. And note that this 0 right here has a parenthesis, because it doesn't touch 0, because that is where our asymptote lies, so it can't do that. And then, like I just said, you have an asymptote at y equals 0. Okay, so from what we just did before, now we have a parent function of 3 to the x. So I'm going to create my xy chart and choose some values that I can graph that would fit within that would have output values that would fit on this graph below. Then what we're going to do is, like I said, we will transform these functions. We are going to transform it. But let's first graph the parent function. Okay, so I plugged in the values -1 to 2, and I got my output values, which shows that this is growth, which makes sense because 3 for b is greater than 1, and I have my horizontal asymptote there. Okay, so let's now look at this translated exponential function to the right. So the first thing I want to point out are over here in this box. I want to state our transformation. So we have x minus 1 in the exponent, which is a horizontal shift, and since we know everything is opposite, this is actually going to be right 1. And then we have a plus 2. Since it's a big number on the outside, this implies it's a vertical shift, so this is up 2. Now, there is one important part of this that we have to note. Any vertical shift, it impacts the asymptote. And you're going to see why in a second. So I usually start by shifting my asymptote, since that's the first thing I graph. So usually, looking at the left, we have it at y equals 0. Well, if I'm going up 2, knowing that any vertical shift changes my asymptote is also going to go up 2. So now, here's my asymptote at the y equals 2 line. So now what you can do is you can still form an XY chart and you can plug them in, but know that you're going to subtract 1 from it first, then take it 3 to that power, and then add 2 at the end. And what I also like to do is also think of it as translating that point that we said always happens in parent functions, that point 0, 1. So if I have 0, 1, and it's usually right here, then since I'm going right 1, that means it would jump over here to the right, and then it would go up 2. So that's where I have a point at 1, 3. Now, to find the values and other points around it, I still will need to create an XY chart, but it's just important to know that since that's a characteristic point that all parent functions of exponential functions have, it will follow the same shifts, just like when we did those characteristic points of 0, 0, and 1, 1 of our commonly used functions in our previous chapter. Okay, so in the top right corner, sorry it's a little messy, I showed my work if you wanted to plug in your x values by hand and find your y values, or you can also use your calculator. Now, the last part we're going to answer is our domain and range. Well, even though it got translated up and right, it still has a domain of all real numbers, negative infinity to positive infinity. So, knowing that, it doesn't matter how you shift it, that's going to be your domain. Now your range, if your range depends where the asymptote is and a vertical shift impacts the asymptote, it also changes the range. So in the parent function, it's usually 0 to infinity, but in this case, since we went up 2, it's going to be 2 to infinity, and again, a parenthesis on that 2 because that's where the asymptote is that the line will never cross.